Hey everyone, welcome back. In the last video, we went deep into Java bytecode. We learned how the source code gets compiled into .class files. We covered a lot of details related to class files, what opcodes are generated, how the JVM interprets all those opcodes at runtime. So naturally, the next step is once we have the class file, how JVM loads that class file, how JVM executes all those class files. And that's what we are going to cover in this video. We are continuing from where we left off. So in this video, we will learn how the JVM loads, links, and prepares the .class file to run them at runtime. By the end of this video, you will have a solid idea of how class loading works in Java. So let's get started. So what is class loading? Class loading is a process by which the JVM locates, reads, and brings the class data, which is the bytecode, into memory for execution. So what happens, suppose when we compile a Java file in a directory, we have the .class file. So in this directory, suppose we have the .class file. So when we run the program, what JVM needs to do, it first needs to locate the file that in this directory, we have the .class file. Once it has the .class file, it has to read the data because we know in the .class file, we have different opcodes. So JVM needs to read that data. And after reading the data, it has to create a runtime representation of that class, that bytecode into the memory. Okay, the memory that gets allocated to JVM when we start a program for the execution. So this is all done under the umbrella of class loading. So in class loading, JVM finds the class, reads the class, and then creates a runtime representation to run the Java code. So whatever we talked about the class loading process, it is divided into 3 steps. The first one is loading. The second one is linking, which is further divided into 3 steps, which is verification, preparation, resolution. And the last one is initialization, where the class will be initialized. So we will cover all these phases one by one. Alright, so the first phase is loading. Let's understand what happens in this stage. So we start with the .java file. When we compile it, we get a .class file. When we run the program, what JVM needs to do first, it has to locate the file because class can be anywhere. It could be present on the directory, it could be present on the network, anywhere. So JVM has to locate the file first. When JVM finds the file, it has to read the data. So it reads the bytecode, then it creates a runtime representation. And that runtime representation is an object of class. All right. Now this class object is stored in the meta space. All right. So it might sound confusing that we are talking about an object of class. What this class is, actually this is present in java.lang.class. And this runtime representation is an object of this class file. We will cover this when we do the dry run. For now, we need to understand that in the loading phase, JVM locates the file, it reads the data present in the .class file, and then it creates the runtime representation, which is an object of class, which is stored in the meta space. So in the loading phase, as a result of the loading phase, we have an object of the class. All right. And this class is nothing but java.lang.class. All right, let's move on. So the next phase is linking. Let's understand what happens in the linking phase. We know linking phase is further divided into 3 steps: verification, preparation, and resolution. So the first one is verification. So what happens in the verification phase, JVM now verifies the bytecode that was loaded or read in the loading phase. Because bytecode itself has a schema, has a syntax, so JVM needs to ensure that the loaded bytecode is correct as per the schema, as per the syntax. Then comes the preparation phase. So what happens in this phase, let's say the bytecode has been verified. Then what happens in the next phase, which is preparation, JVM allocates the default values for static fields. So in case that class has some static fields, so in the preparation phase, the memory will be allocated for those static fields and the default values will be set. So if you have a static variable int, then 0 will be allocated to that int variable. But in the preparation phase, no user code is executed. So it is just allocating the memory for static fields and setting the default values for those static fields. Then comes the resolution phase. In the resolution phase, it resolves the symbolic references. What does it mean? What are the symbolic references? So let me quickly show you the bytecode that we discussed in the last video. So here we have a bytecode from the last video, which was on the bytecode deep dive. And on the screen, we can see the constant pool. Now in this constant pool, you can see many entries which look something like this. All right. So you can see java/lang/string, java/io/printstream. And these are nothing but some class names, some file names, all right? Printstream is a class in the Java library. In the same way, string is another class. So what is happening? These are symbolic references. These are called symbolic references. And you can see there are many symbolic references in this constant pool. Here is another one. All right. So any class that your code refers has a symbolic reference in the generated bytecode in the constant pool. And in this phase, in the resolution phase, what JVM does, it resolves these symbolic references. So in this phase, these symbolic references will be linked to a proper class, in this case print stream class, and this will be resolved and linked with the string class. So this is the resolution phase where all these symbolic references will be resolved. All right. So what happens in the linking phase? Well, the bytecode is verified, then it allocates the memory for the static fields, and in the resolution phase, all these symbolic references are resolved. Let's move on. So this is the last phase, initialization. What happens in this stage is JVM executes static initializers, and in this phase it assigns initial values to all the static fields which are present in the class. Alright, so this is the initialization phase where the class will be initialized. So that completes the high-level overview of the class loading process in Java. But who does that? Well, JVM uses class loaders to load the classes. So that's what we will learn next. We will learn what are class loaders in Java. So class loaders in Java are used to load the classes as part of the class loading process. And in Java, there are three main class loaders. Apart from this, we can also create the custom class loaders. The first one is Bootstrap class loader. This is called Bootstrap because it starts the loading process. It does not have any parent. All right, as we will see soon that class loaders in Java always has a parent. But Bootstrap is a class loader which does not have any parent. When we start the program, JVM loads the required classes, and these classes are present, for example, in the java.base package. So all the core classes like java.util, classes from java.lang are loaded at this stage using Bootstrap class loader. Then we have the platform class loader. Earlier, before Java 9, it used to be called extension class loader, but with Java 9, after Java 9, it has been changed to platform class loader. So what this class loader does, platform class loader loads the classes for other modules. So apart from java.base, we know there are other modules present in the Java library which must be loaded, and all these modules are loaded by platform class loader. So these two class loaders are responsible for loading all the classes, all the required classes apart from your custom classes. All right, and those custom classes or our classes that we write are loaded by the system or the application class loader. The responsibility of the application class loader is to scan the class paths and load the classes from the class path. So this is where our custom classes will be loaded. All right, so there are three class loaders: Bootstrap, platform, and system. Let's move on. So now we will understand a very important concept in the class loading process, that all the class loaders have a parent. So system or the application class loader has a parent, which is the platform class loader. Platform class loader itself has a parent, which is Bootstrap. But Bootstrap is a class loader which does not have any parent. So you can see there is a hierarchy from Bootstrap to system or any custom class loader. We have not mentioned custom, but that would come somewhere over here. We can also create the custom class loaders. So why is there a hierarchy in this case? Now Java by default follows parent first. What that means is whenever we load a class, whenever we run any class, we know the class will be loaded first, and that class will be loaded by a class loader. So when a class loader loads a file, instead of loading the class right away, what it does, it will ask the parent to load it first. It will check with parent first. Only when the parent denies or rejects the request, then only the class loader will load the class. So because it will always check the parent first, that's why this is called parent first hierarchy. So suppose we are running a Java program, and we know to run a Java program, we write Java, then name of the class. And in this case, let's say the name of the class is demo. So when we run this command, we know it will find the class file with name demo, and the code will be executed. Now what will happen, JVM has to load the class first, and this is a custom class. This is present in the class path. So this class loader will be consulted first. All right. Now when system or the application class loader receives a request to load the demo class, it will not load the class immediately. It will ask its parent that, hey parent, do you have the class for the demo? The parent will say, no, I don't, let me check with my parent. So it will go to the Bootstrap. Bootstrap will check its own set, and it will see, because it is only responsible for loading classes from java.base or the core classes. So it knows the pattern of the package. It checks that this is not my package. I am not responsible for this class. So it will say, hey, I don't have this class and I will not load this class. Then the request will come back to the platform. Platform will also see that it is only responsible for loading classes from other Java modules, which let's say have a different package structure. And in this case, we have a custom package structure. So it will also see that, okay, I'm not responsible for loading this demo class. So it will send the response back to the application class loader. And then class loader will see that, okay, platform cannot initialize it, Bootstrap cannot load it. So this is my responsibility that I load this class. So this will load the class demo and this will store the class in its own cache. So when a class loader loads a class, it also stores the class in its own cache. So Bootstrap has its own cache where it stores all the classes that it loaded. Similarly, platform class loader will have its own cache, and similarly, the system class loader will have its own cache. So in this case, when the system class loader loads the demo class, the class will be stored in its own cache. Now the loaded classes are cached so that, let's say, in a running execution, if any other piece of code accesses or references the same class, then JVM does not need to load the same class again because it is present in the cache. So class loader can simply return the cached instance. It does not have to load the class again. So first of all, the class loaders follow the parent first hierarchy. Then they first check the cache. Only if the class is not present in the cache, then only the class will be loaded by a class loader. Alright. So we covered all the class loaders and now we understand the purpose of different class loaders in Java. Let's move on. And now is the time of a quick dry run and we will see what happens when a class is loaded. Because if you remember, we said that a runtime representation of the class is created, which is an object of class, and that class is java.lang.class. So that we will understand as part of the dry run. Alright, so in this example, suppose we have a demo.java file, and when we compile that demo.java file, we get a demo.class file. Then let's say somewhere in the code, we are creating two objects of this demo class, which will be executed later. But first of all, when we run the program, we know this demo class will be loaded by the JVM. Now, what happens when any class is loaded by the JVM? What JVM does, it creates an object of type class. All right. And this object is stored in the meta space. So even though nothing has been created yet, what JVM did after the loading process, it created a new object which is referring to the class object, and what it stores is basically some metadata about your class. Alright, so the class has some metadata and that metadata will be stored in this object and that object will be stored in the meta space. Now what this class is basically, in the java.lang package, we have a class with the name class. So this is confusing, but the name of that file itself is the class. So what JVM is doing, it's creating an object of this file, and that is why this is called a class object. Alright, so any class that JVM loads will have a class object which will be stored in the meta space. Alright, now suppose when the JVM executes this code where it has to create two new objects, so what will happen on the heap? Two new objects will be created. So let's say this is object number 1 and this is object number 2. So D1 reference variable is referring to this object and D2 is referring to this object. But under the hood, they both are demo objects. Alright. And we know these two objects are distinct, they are not equal. And these two are distinct entities on the heap. But the thing is, they both share the same class object which is stored on the meta space. Alright. So no matter what object you create of your class, there will always be one representation, class representation, which will be present in the meta space. So whenever JVM is executing some code and let's say it is interacting with your object, with your class, let's say D1, maybe it is calling a method or accessing a variable, whenever the JVM needs the metadata about any class, it basically references this class object on the meta space. And that is why all the objects of your class will have a single representation which is present in the meta space. They will all share the same class object. All right. So apart from your objects that you create for your class, JVM will always create one additional object of type class, which will be stored on the meta space. And whenever we are, let's say, getting the class, so for example, there are methods like d1.getClass or class name. What JVM does as part of this method, it simply returns this class type. All right. So that is why this is shared among all the objects of a class. So do not get confused. Each class in Java has an object of type class. So each class has a class. All right. And that class, basically this one, is the runtime representation of your class. So in continuation of that dry run, this is the class.java file which I was talking about. So you can see this is present in java.lang package, and name of this file itself is class. So it has a very weird name if you think about it, class.java. That is why all the confusion. And you can see in the documentation that instances of this class, the object that we discussed, which is stored on the meta space, it represents classes and interfaces in a running Java application. All right. So I suggest you go through the documentation of this file. It is very important to be comfortable with this file, because otherwise you won't be able to resolve the confusion. Now, what happens when JVM loads a class? It typically calls the Class.forName method, and it passes the class name, all right, that it needs to load. And that forName method is present in this file. Here it is. So this is that Class.forName method which is used by JVM sometimes to load the classes. And you can see it is basically getting the caller who calls the code, and then it is calling another method forName with caller. So first of all, it gets the class loader of the class that is basically loading another class, and that will be the parent class loader. All right, and then it calls something like this for name 0, and you can see this is a native method. So whenever the class is loaded using class.forName, it has the class name, then it has the parent class loader, and then it calls the native method which will be executed by the JVM. Then internally what it does, it calls the class loader, and here we have the ClassLoader.java, and we can see that this particular method will be called to load the class. And here we have the name and a boolean whether you need to resolve the class or not. So the first thing that you can see is there is a synchronize block, and it is basically taking a lock on the class name. And that is why class loading process in Java is thread safe. So let's say there are multiple threads loading the same class. In that case, only one thread will succeed. So it will not happen that multiple threads will load the same class multiple times. The class will be loaded in the thread safe manner. All right. If the class is loaded, it will be present its cache. If the class is loaded, it does not need to load the class again. But if the class is not loaded, then it will consult the parent class loader if it is present. Otherwise, it will go up to the Bootstrap, or basically its parent. Now, if any parent has the required class, then the class will be returned. But in this case, there we have a check. Let's say if the parent class loaders do not have the class will be still null. And in that case, this particular class loader will have to find and load the class. All right. So that's how classes are typically loaded. This is the overall process, how different classes are involved, how different components are involved in JVM's class loading process. Alright, so here's almost everything that I wanted to cover, and you will find other class loader videos in the same playlist. Feel free to check out. They are slightly old but still relevant. So in this video, we covered how the Java loads your classes from bytecode present on the disk to live objects in the memory, and this is all done using a smart hierarchy of class loaders. Now, if you watched my previous video which was on the bytecode deep dive, then this video completes the full journey from compilation to loading the classes and running them at runtime. But if you haven't seen that one yet, I would definitely recommend to check that out. And in the next video, we will continue our journey on the JVM, and we will cover a very interesting topic. So I will see you in the next one. Thanks for watching.